July 18, 1944, Normandy, France, 08:47 hours. The hedgerow explodes in a shower of dirt and stone. Oberleutnant Klaus Hartmann feels the concussion through the hull of his Panther Osef G, a machine that on paper should dominate any American tank it encounters. Through the cupola periscope, he watches the Sherman emerge from the smoke 100 meters ahead. His gunner has already hit it twice. Clean penetrations. Both rounds struck the turret ring and upper glacis. The Sherman keeps coming. Hartmann's loader is screaming something about ammunition count. His gunner fires again. A third hit, this time on the transmission housing. Sparks cascade off the angled armor. The Sherman's track stutters, grinds, then catches. It pivots left. Its 76mm gun swings toward them with mechanical certainty. Hartmann knows what comes next. He's fought Shermans since Caen. He's killed 11 of them. But this one absorbs punishment like nothing he's encountered before. No catastrophic fire, no cook-off. Just the low, grinding hum of an engine that refuses to die. His radio crackles. Another Panther reports the same phenomenon 2 kilometers south. "They don't burn anymore," the voice says. There's no point fighting them. To understand why those words carried such weight, you must first understand what the Sherman had been. In the spring of 1942, when the M4 Sherman medium tank rolled off assembly lines in Detroit, Lima, and Grand Blanc, it represented American industrial might made manifest. Reliable, mechanically sound, producible in quantities that would flood battlefields from North Africa to the Rhine. But by the winter of 1943, crews had given it another name. The Ronson. After the cigarette lighter. Lights first time, every time. The nickname was born in blood. When an 88mm round from a German Panzer IV or Tiger penetrated the Sherman's armor, the result was often instantaneous and catastrophic. The tank didn't just stop fighting, it erupted. Flames would burst through every hatch and viewport within seconds. Crews called it brewing up. The British termed it lighting a candle. The technical term was ammunition fire. The Sherman carried its main gun ammunition in sponsons, racks mounted along the hull sides and floor, unprotected except by the tank's thin side armor. A single armor-piercing round that penetrated the hull had a high probability of striking stored ammunition. When it did, the propellant charges ignited. Temperatures inside the crew compartment could reach 3,000 degrees Fahrenheit in under 5 seconds. Survival depended on a single factor: exit speed. Tank crews developed rituals. They loosened hatch locks before entering combat. They memorized escape routes in darkness. Drivers kept one hand on the hull release lever at all times. Loaders positioned themselves near the turret hatch, sacrificing firing efficiency for a half-second advantage in evacuation. Some crews refused to load more than 10 rounds at the start of an engagement, accepting reduced combat effectiveness for marginal improvements in survival odds. The statistics were brutal. In the Normandy campaign, U.S. Army Ordnance Department studies documented that 60 to 65% of Sherman losses resulted in complete crew casualties. When a Sherman was penetrated, crew survival rates hovered near 40%. For every 5 tanks knocked out, 2 full crews, 10 men, died in the fire. Replacements arrived at depots in England and were assigned to units that had lost tanks the day before. They could see the burn patterns on the concrete where destroyed Shermans had been dragged for salvage. They could smell the residue. Veteran crews watched the new arrivals with a mixture of pity and statistical calculation. The average combat lifespan of a Sherman crew in heavy fighting was measured in weeks, not months. Tankers became fatalistic. Letters home spoke less of victory and more of odds. Diaries recovered after the war contained repeated references to luck, chance, and the randomness of survival. 1st Armored Division records from the Italian campaign show that entire platoons cycled through 3 or 4 complete crew replacements within a 2-month period. German tankers noticed. Panzer crews reported that American tanks, once hit, rarely required a second shot. Gunnery instructors used the Sherman as an example of proper target priority. Hit it anywhere that penetrates, and the ammunition will do the rest. Disabled Shermans left burning on battlefields served as psychological weapons, columns of black smoke visible for kilometers, marking where American armor had tried and failed. But something else was happening, away from the front lines, improving grounds and research facilities scattered across the American industrial heartland. Engineers at the Aberdeen Proving Ground in Maryland had been collecting data since the North African campaign. Every destroyed Sherman that could be recovered was photographed, measured, and de-analyzed. Ordnance officers interviewed surviving crew members, documenting penetration points, fire initiation times, and escape routes. By late 1942, a pattern emerged that was statistically undeniable. Ammunition placement was the single greatest factor in crew mortality. The solution seemed obvious: move the ammunition. But the Sherman's internal layout had been optimized for production speed and mechanical reliability. Redesigning the hull structure would require retooling factories, halting production, and fielding entirely new vehicles, an option that would cost months of manufacturing output at a time when the invasion of Europe demanded every tank America could produce. The Ordnance Department needed a solution that could be retrofitted, something that didn't require a complete redesign, something that could save crews without stopping the assembly lines. The answer came from an unexpected direction: the Navy. Naval aviators had been dealing with a similar problem since the early days of the Pacific War. Aircraft fuel tanks, when struck by gunfire, ignited catastrophically. Pilots died not from the initial damage, but from the fireball that followed. By 1941, engineers had developed self-sealing fuel tanks, rubber and synthetic compounds that expanded when punctured, automatically closing small holes and preventing fuel leakage. An ordnance engineer named Colonel John K. Christmas proposed adapting the concept, not for fuel — the Sherman's engine compartment was already reasonably protected — but for ammunition storage. The idea was radical in its simplicity: surround the ammunition racks with a liquid jacket. When a penetrating round struck the tank, the liquid would absorb heat, disperse fragments, and flood the ammunition compartment, drowning any incipient fire before it could spread. The liquid had to be non-corrosive, stable across temperature extremes, and compatible with the propellant chemicals used in tank shells. After months of testing, the solution emerged: a mixture of water and ethylene glycol, antifreeze. The system was designated wet stowage. Ammunition racks were enclosed in metal bins with double walls. The space between the walls was filled with the water-glycerin mixture. When the tank was penetrated, even if the round struck the ammunition directly, the liquid jacket would rupture first, flooding the compartment and suppressing combustion. The propellant charges would be soaked before they could reach ignition temperature. Initial tests at Aberdeen in March 1943 showed promise. Engineers fired 50 caliber round into wet stowage racks loaded with live ammunition. The rounds penetrated. The charges got wet. No fires ignited. They escalated to 37mm anti-tank rounds. Same result. By June, they were using captured German 75mm guns at combat ranges. The wet stowage ammunition survived. But there was a complication. The Sherman's hull couldn't accommodate wet stowage racks in the sponson positions without major redesign. The engineers had to relocate the ammunition entirely, moving it from the vulnerable side sponsons to the hull floor beneath the turret basket, where it could be surrounded by the liquid jackets and protected by the tank's thickest armor. This required retooling, but not a complete factory shutdown. Existing Sherman production lines could be modified incrementally. Tanks already in the field could be retrofitted at depot-level maintenance facilities. The process took weeks, not months. In August 1943, the first wet stowage Shermans rolled off the assembly lines. They were designated M4A176W, the W standing for wet stowage. Outwardly, they looked nearly identical to earlier models. Internally, they were transformed. But wet stowage was only part of the equation. Aberdeen engineers had also been studying German armor-piercing rounds recovered from knocked-out American tanks. They noticed that certain types of penetrators, particularly the tungsten-cored rounds fired by late-model German guns, created secondary fragmentation effects inside the crew compartment. Even if the ammunition didn't ignite immediately, fragments would ricochet through the interior at supersonic speeds, killing or wounding crew members and severing hydraulic lines, which then fed the fire. The solution was composite armor layering. Additional steel plates were welded to the hull at critical angles, creating spaced armor that caused incoming rounds to tumble or fragment before reaching the crew compartment. The plates added weight, roughly 1,500 pounds per tank, but they disrupted penetrator performance enough to reduce internal spalling by an estimated 40%. Simultaneously, the Ordnance Department redesigned the Sherman's fire suppression system. Earlier models had relied on handheld CO2 extinguishers, useless in a catastrophic fire. The new system used automatic halon gas dispensers triggered by heat sensors in the ammunition compartment. If the temperature spiked above a threshold, the halon would discharge instantly, smothering combustion before crew members even registered the threat. And there was one more innovation, less dramatic but equally vital: armored ammunition doors. In the original Sherman design, the loader accessed ammunition racks through open bins. If a fire started, it spread instantly throughout the fighting compartment. The new wet stowage tanks featured spring-loaded armored doors on each ammunition bin. The loader would pull a handle, a door would swing open, he'd extract a round, and the door would slam shut automatically. If one bin ignited, the others remained sealed. By November 1943, the U.S. Army had a Sherman that could survive. The first units to receive the upgraded tanks were armored divisions preparing for the Normandy invasion. Crews were briefed on the changes but remained skeptical. They'd heard promises before. They'd been told the Sherman was adequate, that superior numbers and tactics would overcome German armor superiority. They'd buried too many friends to trust engineering reports. The proof would come on the battlefields of France, in the hedgerows and killing fields where German Panzers still held every advantage in firepower and frontal protection. But now, the Americans had something the Germans didn't: tanks that refused to die. The human cost, crew psychology before and after. Sergeant Bill Morrison, a tank commander with the 4th Armored Division, kept a diary throughout the Normandy campaign. His entries from June 1944 are short, clipped, and progressively darker. June 12th. Lost Jenkins's tank today. Panzer IV got him from the tree line. Went up like a torch. June 18th. Don't know the new crew's names yet. Seems pointless. June 24th. We're all dead men. Just a matter of when. By July, his unit received the new wet stowage Shermans. Morrison's entry from July 9th is longer, more detailed. They say the new tanks won't burn. Nobody believes it. Johnson's replacement said he'll believe it when he sees it. I told him he won't live long enough to find out. But something shifted in the weeks that followed. On July 16th, Morrison's tank took a direct hit from a Panther's 75mm gun at 400 meters. The round penetrated the upper glacis exactly where earlier Shermans would have erupted. Morrison's entry from that evening is uncharacteristically detailed. We got hit, I heard it punch through, waited for the fire, nothing. Smoke, yeah, ringing ears but no fire. We backed into cover, checked the interior, the ammo bins were wet, water everywhere. The round went right through the rack, shells were soaked but intact. We reloaded and went back out. Crew psychology transformed measurably. After-action reports from August and September 1944 show a quantifiable decline in evacuation times. Crews in earlier Shermans would abandon the tank at the first sign of penetration, even if no fire had started. Crews in wet stowage tanks stayed at their positions, assessed damage, and continued fighting if the vehicle remained mobile. The difference wasn't courage, it was trust. Trust that the tank wouldn't become their funeral pyre. Tanker Eugene Luciano, a loader with the 2nd Armored Division, described the psychological shift in a 1946 interview. Before the wet tanks, every time you heard metal hit metal, you didn't think. You moved. Hatch, ground, run. You didn't check if there was fire. You assumed there was. After we got the new Shermans, you'd hear the hit and you'd wait. Just for a second, to see if the halon kicked in, to see if water started spraying, and when it did, when you realized you weren't burning, you got angry instead of scared. You wanted payback. That anger translated into combat effectiveness. Crews that survived the first hit were statistically far more likely to score kills on subsequent engagements. They'd learned the tank could take punishment. They pressed engagements longer, maneuvered more aggressively, and accepted risks that would have been suicidal in earlier models. German intelligence reports from late 1944 note the change. A captured document from the 2nd Panzer Division dated October 3, 1944 observes, American tank crews no longer retreat after first contact. They absorb fire and continue advancing. Morale appears high despite material inferiority of their vehicles. Material inferiority. The Germans still believed they had the better tank. They were right, on paper. But they'd failed to account for the human variable. A crew that expects to die fights differently than a crew that expects to survive. The engineering race. How wet stowage worked. The wet stowage system was elegantly simple, but its implementation required solving dozens of micro-engineering problems that never appeared in official reports. Each ammunition bin held between 4 and 6 75mm or 76mm rounds depending on configuration. The bins were constructed from welded steel plate with an outer shell and an inner cradle separated by a 2-inch gap. This gap was filled with the water glycerin mixture, approximately 1.2 gallons per bin. The liquid was held under slight pressure, around 3 psi, just enough to ensure it would spray outward if ruptured. The critical innovation was the bin's internal geometry. Engineers discovered that simply surrounding ammunition with liquid wasn't enough. If a penetrating round struck the bin at a shallow angle, it could pass through the liquid jacket without rupturing it sufficiently to flood the compartment. The solution was to design the bins with internal baffles, thin metal vanes that forced any penetrator to change direction multiple times, guaranteeing maximum contact with the liquid. When a German 75mm APC-BC round struck a wet stowage bin at typical combat velocities, 2,400 to 20,700 feet per second, the sequence unfolded in milliseconds. The penetrator would pierce the outer shell, enter the liquid gap, and fragment against the baffles. The liquid, suddenly depressurized, would explosively vaporize, creating a dense mist that filled the ammunition compartment. Simultaneously, the intact liquid would drain downward, flooding the floor and soaking any propellant charges that had been dislodged. The water-glycerin mixture served multiple functions. Water provided thermal mass, absorbing heat energy from the penetrator and any incipient combustion. Glycerin prevented freezing in European winter conditions and reduced evaporation during long-term storage. The mixture also had fire-suppressing properties. When vaporized, it displaced oxygen in the compartment, further inhibiting combustion. But there were complications. The liquid added weight, approximately 350 pounds per tank when all bins were filled. This reduced the Sherman's already marginal power-to-weight ratio. Crews also had to monitor the bins for leaks. A slow leak over days or weeks could leave a bin partially empty, reducing its effectiveness without any visible warning. Maintenance crews developed field procedures to check liquid levels. A small valve on each bin allowed technicians to verify pressure. If a bin had lost pressure, it could be refilled using standard antifreeze supplies, readily available at any motor pool. This made the system remarkably field sustainable, unlike more exotic solutions that required factory-level support. The system wasn't perfect. If a penetrator struck the ammunition directly rather than passing through the liquid jacket first, the wet stowage could still fail. High-explosive rounds that detonated inside the crew compartment could overwhelm the halon suppression system. And if multiple bins were compromised simultaneously, a rare but possible scenario in close-range engagements, the cumulative effect could exceed the system's capacity. But statistically, wet stowage reduced ammunition fire probability from approximately 60–80% down to 10–15%. That difference represented thousands of lives saved over the final 18 months of the European War. Tactical doctrine shift from knock out the enemy to survive and outlast. The introduction of wet stowage forced a fundamental rethinking of American armor doctrine. Prior to 1944, U.S. tank tactics emphasized mobility and numerical superiority. Sherman units were trained to flank German Panzers using speed and coordination to offset inferior armor and firepower. The doctrine accepted high loss rates as inevitable. Victory would come through attrition, through the ability to replace losses faster than the enemy. But wet stowage introduced a new possibility: tank versus tank engagements where the Sherman could absorb the first hit and return fire. This was revolutionary. Combat reports from the Battle of Arracourt in September 1944, where upgraded Shermans faced superior Panther and Panzer IV forces, show a tactical pattern that would have been unthinkable 6 months earlier. American tank platoons began using bait and anvil tactics. A single Sherman would advance into the open, deliberately drawing fire from German positions. The Sherman would absorb the hit, ideally surviving due to wet stowage and improved armor, while the rest of the platoon, now knowing the enemy's exact position, would flank and destroy the German tank. The tactic worked because American crews trusted their tanks to survive that first critical engagement. German crews, by contrast, remained doctrinally committed to avoiding hits entirely. Panthers would withdraw after missing the first shot, unwilling to expose themselves to return fire. This gave American units tactical initiative despite facing technically superior vehicles. Armored Division commanders began writing new field manuals. The 3rd Armored Division's October 1944 tactical bulletin, marked restricted and distributed only to tank platoon leaders, includes a section titled Exploiting Survivability Advantage. The text reads, "The enemy is equipped with guns that can penetrate our armor at all combat ranges. However, our improved tanks can survive penetration in many cases. Use this advantage. Aggressive positioning and willingness to accept hits in order to secure firing solutions will produce favorable exchange ratios. Willingness to accept hits." That phrase would have been inconceivable in 1943. The doctrine extended beyond tank versus tank combat. Infantry support tactics evolved to exploit the Sherman's newfound durability. Tanks could advance closer to entrenched German positions, absorbing anti-tank fire while infantry maneuvered. The tank became a mobile shield, a rolling piece of cover that infantry squads could use to cross kill zones that had previously been impassable. German defensive tactics struggled to adapt. Panzer Grenadier units reported that American tanks no longer withdrew after being engaged by Panzerfausts or Panzerschrecks at close range. If the hit didn't immobilize the tank, it would continue advancing, systematically destroying infantry positions with machine gun and high explosive fire. The psychological effect on German infantry was profound. Their most reliable anti-tank weapons no longer guaranteed results. But the doctrine had limits. Wet stowage didn't make the Sherman invincible. A well-placed 88mm round from a Tiger or King Tiger could still catastrophically destroy any Sherman variant. German tank destroyers like the Jagdpanther remained lethal at long range. And in the close terrain of urban combat, Aachen, Metz, the Hürtgen Forest, where engagement ranges collapsed to under 100 meters, even wet stowage couldn't always save crews from the massive kinetic energy of German high-velocity guns. Still, the tactical paradigm had shifted. American armor doctrine was no longer built on the assumption of inevitable catastrophic losses. It was built on survival, endurance, and the grinding calculus of industrial attrition, a calculus where the Americans held every advantage. German perspective. Intelligence reports, captured tank analysis, crew testimonies. The Germans first noticed something had changed in August 1944 during the counteroffensive at Mortain. Panzer Brigade II, equipped with newly delivered Panther OSF-Gs, engaged elements of the U.S. 3rd Armored Division in a series of close-range tank duels along the approaches to Hill 285. German after-action reports document multiple instances where Panthers scored confirmed penetrating hits on advancing Shermans, strikes that should have resulted in immediate destruction. Instead, the Shermans continued fighting. A report filed by Hauptmann Ernst Fischer comments, Der 5th Company noted with clinical precision, at 0640 hours, our lead platoon engaged 6 enemy medium tanks at 800 meters range. 3 confirmed penetrations were observed, 2 on turret faces, 1 on frontal glacis. Expected secondary explosions did not occur. Enemy tanks returned fire effectively. 2 of our vehicles were disabled. Remaining enemy tanks withdrew in good order, maintaining formation integrity. The phrase, expected secondary explosions did not occur, appears repeatedly in German combat reports from late summer 1944. Panzer crews had been trained for 3 years to expect American tanks to brew up after penetration. The absence of that catastrophic fire signature disrupted German gunnery doctrine. Tank commanders couldn't confirm kills visually. They had to assume disabled Shermans might return to action after field repairs. By September, German intelligence had captured several upgraded Shermans. The Waffenprüfamt, the Wehrmacht's weapons testing agency, conducted detailed technical analysis at the Kummersdorf Proving Ground south of Berlin. Their report, dated September 18, 1944, identifies the wet stowage system with remarkable accuracy. The document describes liquid-cooled ammunition storage compartments designed to suppress combustion following armor penetration. It notes the relocation of ammunition from sponsons to hull floor, the armored bin doors, and the automatic fire suppression system. The analysis concludes with an assessment that borders on resignation. The enemy has effectively negated our primary advantage in tank combat, the ability to achieve catastrophic kills with first-round hits. Engagement doctrine must be revised to account for enemy vehicles requiring multiple penetrations to achieve mission kill. Multiple penetrations. That was the death knell for German armor in the West. The Panzer divisions simply didn't have the ammunition, fuel, or time for prolonged engagements. German tactical doctrine had always emphasized decisive, overwhelming first strikes, quick penetrations followed by rapid disengagement before Allied artillery could respond. A Sherman that survived the first hit and continued fighting disrupted that entire tactical framework. Crew testimonies from captured German tankers reveal the psychological dimension. An interrogation report from the 12th SS Panzer Division, dated November 3, 1944, includes testimony from Oberscharführer Dieter Kluge, a Panther commander with 15 confirmed kills. We were told the American tank was inferior. This is true for the gun, for the armor thickness, but it no longer matters. You hit them, you see the strike, and they keep coming. Our commanders tell us to hit them again. But in the time it takes to reload, they have flanked you. or their artillery has found you. The American tank is not better, but it survives. And survival is everything. Survival is everything. Coming from a veteran Panzer commander, those words carried immense weight. German tank production could not match American output even at its peak in 1944. When Germany produced one Panther, America produced 5 Shermans. But if each Panther could destroy 3 or 4 Shermans before being knocked out, the mathematics favored Germany. Wet stowage broke that equation. If Shermans survived the first engagement, if they could be repaired and returned to service, if crew survival meant veteran experience accumulating rather than being constantly lost, then numbers became overwhelming. By December 1944, German training manuals were advising Panzer crews to aim for specific weak points on the Sherman: transmission housing, turret ring, lower hull plate, locations where penetration might still produce catastrophic results despite wet stowage. But these were smaller targets, harder to hit, especially at long range or in poor visibility. The Germans were being forced to fight more precisely, more carefully, at exactly the moment when the Eastern Front was collapsing and the Western Allies were grinding toward the Rhine. They no longer had the luxury of careful gunnery, but the alternative, trading shots with wet stowage Shermans at close range, was increasingly suicidal. It was a trap with no escape. The numbers game, production versus quality, American logistics advantage. In January 1944, American factories produced 1,821 M4 Sherman medium tanks. In January 1945, production had declined to 1,120 units, not because of reduced capacity, but because fewer Shermans were being destroyed. The wet stowage revolution transformed the mathematics of armored warfare in ways that extended far beyond crew survival. Every tank that survived an engagement was a tank that didn't need to be replaced. Every experienced crew that lived to fight another day was a crew that didn't need months of training. Every spare part, every gallon of fuel, every 76mm round that went into a repaired tank rather than a new one multiplied American logistical efficiency. The U.S. Army calculated the full life cycle cost of a Sherman at approximately $85,000 in 1944 dollars, roughly $1.5 million in modern terms. That figure included the tank itself, ammunition load, spare parts, crew training, and transportation to the European theater. When a Sherman brewed up, all of that investment vaporized in seconds. Wet stowage reduced loss rates from combat by an estimated 35 to 40% in the final year of the war. Across the roughly 20,000 Shermans deployed in Europe between June 1944 and May 1945, that translated to approximately 7,000 tanks that survived engagements they would have been lost in earlier. At $85,000 per tank, wet stowage saved the U.S. Army nearly $600 million, enough to fund entire additional armored divisions. But the numbers became even more favorable when accounting for crew experience. A replacement tank crew in 1944 required approximately 6 months of training before deployment: basic training, armor school, unit integration, and tactical exercises. An experienced crew that survived multiple engagements developed skills that couldn't be taught in training: target recognition speed, instinctive gunnery adjustments, terrain reading, and the 1,000 micro-decisions that separated effective tankers from casualties. Personnel records from the 4th and 6th Armored Divisions show that by March 1945, more than 60% of tank commanders had been with their units for at least 4 months, a dramatic increase from the 20 to 30% continuity rates observed in 1943. This accumulation of veteran experience created a multiplier effect. Experienced crews killed enemy tanks at roughly 3 times the rate of replacement crews and suffered losses at half the rate. The logistical impact extended to maintenance and repair operations. Tanks disabled by fire required complete replacement. There was nothing salvageable from a vehicle that had burned at 3,000 degrees. Tanks disabled by penetration but saved from fire could often be repaired at field maintenance level. Engine swaps, transmission replacements, turret ring repairs, all were feasible if the hull hadn't been gutted by flame. Ordnance companies in France and Belgium processed damaged Shermans on an industrial scale. A tank that took a penetrating hit in the morning could be repaired and back in action within 48 to 72 hours if the internal fire had been suppressed. This created a float of combat-ready vehicles that exceeded the number actually assigned to frontline units. Divisions could sustain offensive operations longer, push harder, and accept tactical risks because they knew damaged tanks would return. Germany possessed no equivalent system. When a Panther was disabled, it often had to be transported hundreds of kilometers to rear area workshops, if it could be recovered at all. Allied air superiority made daylight vehicle recovery almost impossible. Disabled German tanks were frequently destroyed by their own crews to prevent capture, even if the damage was repairable. The Americans could afford attrition. The Germans could not, and wet stowage widened that gap to an unbridgeable chasm. By the spring of 1945, some American armored divisions were reporting tank availability rates above 90%, meaning 9 out of every 10 authorized tanks were combat-ready at any given time. German Panzer divisions were operating at 30 to 40% availability, crippled by lack of spare parts, fuel shortages, and the cumulative losses of 2 years of retreating warfare. The Sherman had become more than a weapon. It had become a logistical ecosystem, one that survived, adapted, and multiplied while its enemies withered. Technological convergence, British contributions, Soviet observations. The American wet stowage innovation didn't occur in isolation. Allied collaboration, formal and informal, accelerated the development and refinement of tank survivability technologies across all Western Allied forces. The British had been grappling with the same ammunition fire problem in their own tank designs, particularly the Cromwell and Churchill models, both of which suffered from poorly protected ammunition stowage. British tank crews in North Africa had developed field expedient solutions as early as 1942, packing sandbags and spare track links around ammunition bins to provide additional protection. When American ordnance officers shared the wet stowage concept with British counterparts in early 1943, the British tank mission at Aberdeen Proving Ground contributed critical refinement. Some British engineers had extensive experience with fire suppression chemistry from their work on naval vessels and aircraft. They recommended modifications to the water-glycerin mixture ratio, improving its performance in extreme cold, a consideration American engineers focused on North African and Mediterranean conditions had underweighted. The British also contributed armor metallurgy insights. British steel mills had developed face-hardened armor plate that was more resistant to spalling, the internal fragmentation that occurred when armor was struck but not penetrated. This technology was shared with American steel producers, and by mid-1944, Sherman hulls were being manufactured with improved armor quality that complemented the wet stowage system. The result was a hybrid design philosophy. Shermans produced after August 1944 incorporated American wet stowage, British armor metallurgy, and fire suppression chemistry developed through Anglo-American collaboration. The British applied similar innovations to their own Sherman variants. The Sherman Firefly, armed with the formidable 17-pounder anti-tank gun, received wet stowage retrofits that made it one of the most survivable Allied tanks of the war. Soviet observers, meanwhile, took a characteristically different approach. The Red Army received thousands of Lend-Lease Shermans, and Soviet tank crews quickly recognized the wet stowage advantage. However, Soviet industrial priorities focused on maximizing production volume over survivability enhancements. The T-34, the Red Army's primary medium tank, never received wet stowage or equivalent systems. Soviet doctrine accepted high crew casualty rates as inevitable. Tank crews were considered replaceable. Tanks were precious. This brutal calculus was reflected in Red Army training, which emphasized aggressive, almost reckless tactics that sacrificed crew survival for tactical momentum. Soviet tankers had a dark joke. The tank is steel, the crew is meat. There is always more meat. But Soviet tank design bureaus studied captured German intelligence on wet stowage Shermans with great interest. Post-war Soviet tank designs, the T-54, T-55, and T-62, incorporated ammunition isolation concepts derived directly from the Sherman's wet stowage system. Soviet engineers enclosed ammunition in armored bins and relocated it to less vulnerable positions within the hull. These innovations would influence Cold War tank design for decades. The technological convergence extended beyond armor. American, British, and Canadian forces shared intelligence on German anti-tank weapons, pooling data to develop countermeasures. When German forces introduced the Panzerfaust 60 and 100 infantry portable shaped charge weapons capable of penetrating Sherman armor, Allied ordnance officers collaborated on applique armor solutions. Sandbags, spare track links, and concrete composite panels became standard field modifications, applied by crews using shared technical bulletins that circulated through all Allied armies. This collaborative environment accelerated innovation cycles. A field modification, and developed by a Canadian tank unit in Italy, might be tested by American engineers at Aberdeen, refined with British metallurgical input, and distributed across all Allied forces within weeks. The Germans, by contrast, operated in increasing isolation, their development bureaus fragmented and competing for shrinking resources. The Sherman's wet stowage system became a symbol of Allied technological cooperation, a demonstration that shared knowledge and integrated industrial capacity could overcome individual technical shortcomings. The Allies didn't build the best tank of World War II, but they built a tank that evolved, survived, and ultimately overwhelmed an enemy that fielded technically superior but strategically unsustainable designs. September 19, 1944. Arracourt, France. The field south of Arracourt stretched flat and featureless under a gray autumn sky. It was perfect tank country, open, firm ground with clear sight lines extending for kilometers. And that morning, it belonged to the Germans. Combat Command A of the U.S. 4th Armored Division, one of the most experienced American armored units in France, held a thin defensive line along a north-south axis between the villages of Arracourt and Rechicourt. They were outnumbered, outgunned, and facing one of the most formidable mechanized forces the Wehrmacht could still field, the 5th Panzer Army, spearheaded by Panzer Brigade 111 and elements of the 113th Panzer Brigade. The German force included more than 160 panzers, primarily Panther Osif Gs and Panzer IVs, supported by assault guns and mechanized infantry. Their objective was to smash through American lines, recapture the Moselle River crossings, and destabilize the entire Third Army front. Against them, Combat Command A fielded 47 M4A3 Shermans. Nearly all were wet stowage variants equipped with 76mm guns and the full suite of survivability enhancements developed over the previous year. At 06:15 hours, the German attack began. Panzer Brigade 111 advanced in a broad formation, Panthers leading, moving at speed across the open ground. American forward observers reported the enemy column at 06:22 hours. By 06:30, German Panzers had reached firing positions 200 meters from the American line. The Panthers opened fire. At that range, their 75mm KDUK-42 guns could penetrate any Sherman ever built. The first salvo struck home. 3 Shermans hit almost simultaneously. Crews braced for the characteristic fireball. It didn't come. One Sherman lost its track and slewed sideways, immobilized but intact. Another took a hit to the turret that jammed the gun traverse, but the crew remained alive inside, already radioing coordinates to supporting artillery. The third absorbed a penetration through the upper glasses, exactly where the wet stowage bins were located. The crew felt the impact, heard the water spray, smelled the halon discharge. The tank stayed in the fight. American return fire began within seconds. The 76mm gun couldn't reliably penetrate a Panther's frontal armor at 1,200 meters, but American crews had learned to aim for tracks, gun barrels, and optical equipment, mobility kills and mission kills rather than catastrophic kills. 2 Panthers lost tracks in the opening exchange. A third took a round through the gun mantlet that disabled its main armament. The German advanced stele led Panzer commanders trained to expect rapid breakthrough after the initial barrage found themselves trading fire with an enemy that refused to collapse. The Americans weren't retreating. Damaged Shermans were reversing into hull-down positions, maintaining fields of fire while presenting minimal target profiles. Intact tanks were maneuvering laterally, using terrain folds that didn't provide cover but broke up German firing solutions. By 0700 hours, the engagement had devolved into a grinding exchange at medium range, exactly the type of fight German doctrine sought to avoid. Panthers had superior guns and armor, but American numbers and survivability were neutralizing those advantages. Then the American artillery arrived. Forward observers, many positioned in disabled but still functional Shermans, had been calling fire missions since the engagement began. At 0705, the first salvos of 105mm and 155mm high-explosive shells impacted the German formation. Panthers could shrug off tank fire, but they couldn't ignore massed artillery. Crews buttoned up, visibility dropped, coordination deteriorated. American tank platoons, seeing the German formation disrupted, counterattacked. It was a calculated risk, advancing into the teeth of superior German firepower. But the American commanders understood something fundamental. Their Shermans could survive hits that would have been fatal 6 months earlier. They could trade shots, absorb damage, and keep fighting long enough for numbers and artillery support to decide the engagement. 3rd Platoon, Company C, led by Lieutenant James Leach, advanced directly into the German center. Leach's after-action report describes the attack with clinical precision. We took fire at 800 meters. 2 of my tanks were hit. Both continued advancing. At 600 meters, we achieved flanking positions on the enemy lead elements. We engaged at near point-blank range. 3 enemy tanks destroyed, 2 disabled. My own tank was struck twice during the engagement. We remained combat effective throughout. We remained combat effective throughout. That sentence encapsulates the transformation wet stowage had created. By 0800 hours, Panzer Brigade 111 had lost 27 tanks, destroyed, disabled, or abandoned. The American line had bent but not broken. German commanders ordered a tactical withdrawal to regroup and reassess. They would attack again over the following 6 days. Each assault followed the same pattern. Initial German advantage, American absorption of damage, grinding exchange, artillery intervention, German withdrawal. By September 25th, when the battle finally ended, German forces had lost more than 80 Panzers. American losses totaled 31 Shermans destroyed, but of those, only 14 were total losses. The remaining 17 were recovered, repaired, and returned to service. The kill ratio traditionally weighted in Germany's favor had reversed, and more importantly, the psychological calculus had shifted irreversibly. The true turning point at Arracourt wasn't tactical, it was psychological and strategic. German intelligence officers. ICERs analyzing reports from the battle recognized they were facing a fundamentally different opponent. A captured 5th Panzer Army intelligence summary dated September 27, 1944 states, American medium tank survivability has increased dramatically. Confirmed penetrations no longer guarantee kills. Engagement duration has extended beyond acceptable limits for our tactical doctrine. Current ammunition and fuel constraints cannot sustain prolonged tank engagements. Recommend revised operational approach prioritizing ambush tactics and prepared defensive positions. Revised operational approach. That was Wehrmacht bureaucratic language for, we can't fight them head-on anymore. Panzer commanders who had operated with near impunity in 1943, men like Obersturmbannführer Rudolf von Ribbentrop, whose 5th Company of the 1st SS Panzer Regiment had destroyed dozens of Shermans in Normandy, were now filing reports that bordered on defeatism. Von Ribbentrop's September 30th combat assessment includes a passage that German High Command found so demoralizing they restricted its distribution. The American tank remains inferior in direct combat capability. However, the enemy has achieved parity through survivability engineering. Our tactical advantage, rapid decisive engagement, has been neutralized. Without the ability to achieve catastrophic first-round kills, we cannot exploit our qualitative superiority before enemy numerical superiority and artillery support overwhelm local engagements. Translation: we can still kill them, but not fast enough. The impact rippled across the entire Western Front. Panzer divisions that had operated offensively since 1940, striking, destroying, advancing, were being forced into defensive postures. The vaunted German armored doctrine, built on mobility and shock effect, was collapsing under the weight of an enemy that could absorb punishment and grind forward relentlessly. At Arracourt, this manifested in measurable behavioral changes. On September 21st, during the 3rd day of fighting, American reconnaissance elements observed German Panthers withdrawing after scoring confirmed hits on advancing Shermans, hits that didn't produce the expected catastrophic fires. Panther commanders, trained to verify kills before disengaging, couldn't waste ammunition on targets that might survive, but they also couldn't afford to remain in position long enough to fire multiple rounds while American artillery zeroed their locations. The result was hesitation, and in armored warfare, hesitation is fatal. American tank crews, sensing the shift, became more aggressive. Combat reports from the final 3 days of Arracourt describe Sherman platoons pursuing withdrawing Panthers, a reversal of the tactical dynamic that had dominated earlier engagements. Shermans couldn't reliably kill Panthers from the front, but a Panther in retreat exposed thinner rear armor. American crews began scoring mobility kills and engine compartment penetrations on enemy tanks that weeks earlier would have been untouchable. The numbers told the story. On September 19th, the first day of battle, German forces achieved a 2.5-to-1 kill ratio. Every American tank destroyed cost Germany 2.5 Panzers, a sustainable exchange given superior German armor. By September 25th, that ratio had collapsed to nearly 1:1, and when accounting for repaired and returned Shermans, the EF-ball stiff exchange ratio favored the Americans at 1:1.5. Germany was losing a battle of attrition in the West for the first time since 1940. But the psychological impact extended beyond the battlefield. German tank crews began refusing to engage under unfavorable conditions. Instances of Panthers withdrawing before making contact, unthinkable in 1943, appeared with increasing frequency in after-action reports. Crew morale assessments, collected through frontline unit political officers, documented widespread fatalism. One report from an SS Panzer division operating near Metz in October 1944 includes anonymous crew testimony. "We are told we have the superior tank. This is true, but it does not matter. The Americans have 10 tanks for every one of ours. And now, when we destroy one, it returns the next day. How do you win such a war?" How do you win such a war? That question had no answer. The German military had been built on a doctrine of qualitative superiority overcoming quantitative disadvantage. Elite training, superior equipment, and aggressive tactics would defeat larger but less capable forces. That doctrine had worked in Poland, France, and the early years on the Eastern Front. But wet stowage broke it. When the qualitative advantage, the ability to achieve quick, decisive kills, disappeared, all that remained was the quantitative reality, and in that contest, Germany had already lost. By November 1944, German armored formations on the Western Front were operating under explicit orders to avoid tank versus tank engagements unless absolutely necessary. Panthers and Tigers, which had once hunted Allied armor, were now relegated to defensive strongpoints and ambush positions. The psychological transformation was complete. German tank crews who had terrorized Allied armor for 2 years now feared prolonged engagement with an enemy they still considered technically inferior. The Americans had achieved something remarkable, not through superior firepower or thicker armor, but through engineering that turned survival into a weapon. At Arracourt, 47 wet stowage Shermans had fought 160 German Panzers to a standstill and ultimately forced their withdrawal. It was a tactical victory, certainly, but more than that, it was proof of concept. The Sherman wouldn't outfight the Panther, but it would outlast it. And in industrial warfare, that was the only advantage that mattered. The data emerged slowly, compiled from after-action reports, maintenance logs, and crew debriefings across dozens of armored divisions. By January 1945, U.S. Army Ordnance had assembled a statistical portrait of wet stowage performance that exceeded even optimistic projections. Crew survival rates in penetrated wet stowage, Shermans, 85%. That single figure represented a revolution. In 1943, when a Sherman took a penetrating hit, 4 out of 10 crew members died. Now, in vehicles equipped with wet stowage, 15 out of 17 survived. The transformation saved approximately 4,000 American tank crewmen's lives between June 1944 and May 1945, men who would have burned to death in earlier model Shermans. But survival was only the beginning of the impact. Tank recovery and repair rates told an equally important story. Pre-wet stowage, approximately 70% of Sherman losses were classified as total write-offs, vehicles so catastrophically damaged by internal fires that no salvageable components remained. Post-wet stowage, that figure dropped to 35%. More than half of all knocked-out Shermans were now repairable at field or depot-level maintenance facilities. This created a multiplication effect in combat power. The 3rd Armored Division, heavily engaged throughout the campaign from Normandy to the Rhine, officially had 232 M4 Shermans on its table of organization. Maintenance records show that between August 1944 and March 1945, the division actually fielded more than 280 tanks in combat. The excess represents. Unding repaired vehicles returned to service faster than new replacements arrived from rear depots. The Germans possessed no equivalent capacity. Wehrmacht vehicle recovery doctrine required disabled tanks to be transported to rear area workshops, often hundreds of kilometers from the front. Allied air superiority made daylight recovery operations nearly suicidal. Disabled Panthers and Tigers were frequently destroyed in place to prevent capture, even when damage was repairable. At the Battle of the Bulge in December 1944, this disparity became strategically decisive. German forces committed more than 200 armored vehicles to the offensive, the largest concentration of German armor on the Western Front since 1940. American units, many equipped with wet stowage Shermans, absorbed devastating initial attacks. Dozens of tanks were knocked out in the opening days of the offensive, but those tanks didn't disappear from the order of battle. Ordnance companies, working through the chaos of the German breakthrough, recovered and repaired disabled Shermans at unprecedented rates. A Sherman hit on December 17th might return to combat by December 20th, 3 days from battlefield casualty to frontline service. German vehicles disabled on December 17th were, at best, weeks from repair and more often were abandoned as the offensive collapsed. By December 26, when the German attack had stalled and American counteroffensives began, effective tank strength ratios had shifted dramatically. German armored units reported availability rates below 40%, meaning fewer than half their authorized vehicles were combat-ready. American armored divisions maintained 75 to 80% availability throughout the battle. The strategic calculus was brutal. Germany's final offensive had consumed irreplaceable armor assets while the Americans continuously regenerated combat power. But the impact extended beyond numbers. Crew experience accumulation, the human capital gained when veteran tankers survived, created a compounding advantage. By early 1945, many American tank platoons consisted entirely of crews with 4 or more months of continuous combat experience. They had learned terrain reading, target priority, instinctive gunnery adjustments, and the 1,000 micro-skills that separated effective tankers from casualties. Sergeant Bill Morrison, whose diary entries from June and July 1944 documented the psychological transformation wet stowage created, survived the war. His final entry, dated May 7, 1945, the day Germany surrendered, is brief. "We made it, all 5 of us. Same crew that landed in Normandy. The tank saved us every time." Morrison's crew represented a statistical miracle. Of tank crews that landed in Normandy in June 1944 and fought continuously through May 1945, fewer than 15% completed the entire campaign with their original crew intact. Morrison's crew was part of that tiny fraction, 5 men who had survived 11 months of combat in a vehicle that, by all traditional metrics, should have been their coffin. German tankers had no equivalent stories. Panzer crew rotation rates, driven by catastrophic loss rates and equipment shortages, meant few crews stayed together for more than a few weeks. Veteran Panzer commanders, men with years of combat experience, were increasingly commanding hastily trained replacement crews in vehicles that lacked spare parts and adequate fuel. The qualitative advantage had inverted. By spring 1945, the average American tank crew had more combat experience than their German counterparts, operated more reliable equipment, and fought with the confidence that came from knowing their vehicle would protect them. The Sherman, once mocked as the Ronson lighter, had become the most survivable tank in the European theater, not through thicker armor or bigger guns, but through engineering that prioritized the crew over the machine. The strategic consequences of wet stowage extended far beyond individual battles or crew survival statistics. The technology fundamentally altered the economics of armored warfare in ways that shaped the final months of the European campaign. In traditional tank versus tank engagements, the side with superior vehicles could accept numerical inferiority because each of their tanks could destroy multiple enemy vehicles before being knocked out. German doctrine throughout 1942 and 1943 operated on this principle. 1 Tiger or Panther was worth 3 or 4 Shermans. This exchange ratio, if sustainable, would allow Germany's smaller tank production to offset American industrial capacity. Wet stowage destroyed that calculus. When Shermans stopped burning, when damaged tanks could be repaired and returned to service, when crews survived to fight again with accumulated experience, the exchange ratio became irrelevant. Even if a Panther destroyed 2 Shermans before being knocked out, those 2 Shermans might return to combat within days while the Panther remained a total loss. This forced Germany into a strategic death spiral. Panzer divisions unable to achieve decisive tactical victories were ground down through attrition. Commanders who had operated offensively for years found themselves relegated to defensive holding actions, trading space for time while waiting for reinforcements that never arrived. The psychological impact on German leadership was profound. Albert Speer, Minister of Armaments and War Production, noted in his post-war memoir that by late 1944, German tank production had reached its highest levels of the war, approximately 1,500 Panzers per month. But this industrial achievement was meaningless. Tanks were being destroyed faster than they could be replaced, and crew training couldn't keep pace with losses. Speer's diaries from December 1944 include a stark assessment. "We produce tanks faster than the Americans, but they lose tanks slower than we do. In this difference lies the entire trajectory of the war." American armored commanders, recognizing their survivability advantage, adopted increasingly aggressive operational tempos. The rapid advances of Patton's Third Army across France in August and September 1944, Operations that outran supply lines and pushed armored spearheads deep into German-held territory were possible only because American tank losses remained sustainable. Divisions could accept high engagement rates because disabled vehicles returned to service quickly and crew casualties remained manageable. German forces, by contrast, became increasingly conservative. Panzer divisions that once spearheaded offensive operations were parceled out in battalion and company-sized packets to shore up collapsing defensive lines. Armor, which should have been concentrated for counterattacks, was instead scattered across hundreds of kilometers of front, defending everywhere and decisive nowhere. This strategic fragmentation was visible in combat reports from the Rhineland campaign in February and March 1945. American armored divisions routinely encountered German armor in small, isolated groups, a platoon of Panthers defending a bridge, a company of Panzer IVs covering a retreat route. These units fought skillfully and inflicted casualties, but they lacked the mass to achieve operational effect. The Americans, meanwhile, operated armored divisions at full strength, with tank availability rates consistently above 80%. When the 4th Armored Division broke through German lines at Oppenheim in late March 1945, it did so with more than 200 operational tanks, a level of combat power German Panzer divisions hadn't fielded since the Ardennes offensive 3 months earlier. But the most profound impact was invisible. It existed in the decisions not made, the attacks not launched, the risks not taken. German commanders, aware that tank engagements would result in unsustainable attrition, avoided combat whenever possible. American commanders, confident in their tank's survivability, sought engagement aggressively. This created a feedback loop. German forces withdrew to avoid attrition, ceding territory and operational initiative. American forces advanced into the vacuum, seizing crossings, cutting supply lines, and fragmenting German defensive coherence. Each German withdrawal made the next engagement less favorable, while each American advance improved their logistical position and concentration of force. By April 1945, entire German army groups were collapsing not through decisive battlefield defeat but through cumulative exhaustion. Units simply disintegrated, crews abandoned vehicles, infantry surrendered en masse, command structures evaporated. The Wehrmacht hadn't been destroyed in climactic battles. It had been worn away through 1,000 small engagements where American armor survived, adapted, and returned, while German armor died and was never replaced. A captured German intelligence report from late April 1945, recovered near the Elbe River, contains a passage that serves as epitaph for German armored doctrine. The enemy has negated our technical advantages through superior logistics and vehicle survivability. We can still win individual engagements. We cannot win the campaign. Recommend cessation of armored operations to preserve remaining equipment for negotiated settlement. The report was dated April 25, 1945. 15 days later, Germany surrendered unconditionally. Wet stowage hadn't won the war. No single technology ever does. But it had accelerated the end, saved thousands of lives, and demonstrated a fundamental principle that would shape military technology for generations. Survivability is a weapon system. The Sherman that had been mocked, that had burned on battlefields from North Africa to Normandy, had evolved into something its critics never anticipated. A tank that refused to die, crewed by men who learned they could survive, fighting an enemy that discovered superior firepower meant nothing against an opponent who could absorb punishment and keep coming. In the end, that was the lesson of wet stowage. The tank that survives longest wins. The wet stowage Sherman never became legendary. It doesn't occupy the same cultural space as the Tiger, the Panther, or even the later American designs it inspired. Historians debate its combat effectiveness. Veterans argue about whether it was adequate. The controversies persist because the Sherman's true achievement was invisible. It was a tank that succeeded by refusing to fail catastrophically. War is often decided not by the most powerful weapon, but by the weapon that remains functional when the battle is longest and most desperate. The Sherman, equipped with wet stowage, embodied this principle. It absorbed hits that should have been fatal, protected crews who should have died, and returned to combat when conventional wisdom said it should have been scrap metal. The philosophy survived long after the last Sherman was retired. Modern main battle tanks, the M1 Abrams, the Israeli Merkava, the German Leopard 2, all incorporate blowout ammunition panels, fire suppression systems, and crew survivability features directly descended from wet stowage technology. The principle is identical. Protect the crew first because a tank without a crew is useless. but a crew that survives can fight again. There's a memorial in Bastogne, Belgium, where the battles of the Bulge raged in December 1944. Among the preserved vehicles is an M4A3 Sherman, turret number 23, that took 4 penetrating hits during the defense of the town. It didn't burn. The crew survived. They repaired it and fought through to Germany. Next to the tank is a plaque with 5 names, the crew that brought it home. All 5 men lived into their 70s and 80s. They attended reunions, told their stories, and insisted the Sherman wasn't the best tank of the war. But it was the tank that saved them. And in the arithmetic of war, where every equation ends in lives lost or preserved, that was the only metric that truly mattered. The German tank crews who said there's no point fighting weren't admitting defeat by enemy superiority. They were acknowledging something more fundamental, that in a war where attrition is inevitable, the side that survives longest wins. The Sherman, through wet stowage and the engineering philosophy it represented, had become unbeatable not because it destroyed everything it faced, but because it refused to be destroyed. That refusal, multiplied across thousands of tanks and tens of thousands of crewmen, changed the trajectory of history, one survived engagement at a time.